All right, so my name is Matthew Bergens, and I will be presenting on papillary thyroid carcinoma. My slide was made in BioRender before the presentation template was sent out, so that's why it looks a little different. I just didn't want to redo it. Um, all right, so starting off, I will first introduce papillary thyroid carcinoma, then we'll talk a little bit about the endocrine pathway, we'll talk a little bit about tumor cells, big picture, then we'll look at the cell signaling, and then we'll talk about the treatment for it. So first thing, papillary thyroid carcinoma, or PTC, is a cancer of the thyroid gland. The thyroid gland is that lobe, which you can see right here, kind of looks like a butterfly, and it's part of the endocrine system. Carcinoma being a cancer of epithelial cells, or cells that line the internal organ. So the specific cells that are within the thyroid that this cancer comes from are considered epithelial cells in origin. There's four types of thyroid cancer. I'll be focusing on papillary, but the other types, just for FYSA, are papillary, follicular, medullary, and anaplastic. And I put them in an order that is generally from the best prognosis to the worst prognosis. The most well differentiated cancers, i.e., the cancers that look most like the original tissue, to the cancers that have lost the receptors, have lost the cell specificity, and are thus more difficult to treat, like anaplastic, for instance. So papillary thyroid carcinoma, it's generally slow growing, generally easy to treat. It has some of the best 5-year survival rates for patients. Patients generally receive surgery, radiotherapy, and then thyroid hormone supplementation for the rest of their lives. But we'll discuss this in a little bit more detail later. So you can see here that the cancer will generally appear in one lobe. One of the two lobes, it will grow. With time, it can metastasize to the nearby blood vessels, as well as the lymphatics and a lot of lymph nodes that are in this area. And so moving to number 2, we have the HPT axis. So the HPT axis is the endocrine axis that has to do with the thyroid. And so it starts off with the hypothalamus. You can see right here, the paraventricular nucleus of the hypothalamus will release thyroid releasing hormone, or thyrotropin releasing hormone, TRH. This will travel through the hypophyseal network and then lead to the pituitary gland, the anterior pituitary, where it will act on the neurosecretory cells there, which will in turn release thyroid stimulating hormone. Thyroid stimulating hormone will head to the blood and will eventually find its way to the thyroid, where it will bind to the receptors on the thyroid and then induce the creation of the thyroid hormones, T3 and T4. You can see right here that I've included a picture of what T3 looks like, and then it's missing a fourth iodine right here in this position, on this aromatic ring. And if you add an iodine there, it just becomes T4. So that's really the only molecular difference. And then from there, thyroid hormone will be released into the blood. It will travel throughout the body, diffusely act on the target tissues. Um, Interestingly, the thyroid cells themselves are the only cells that uptake iodine. Think about the sodium iodine cotransporters that we learned earlier about in the semester. And then thyroid hormone, which is important to, when we think about the larger context of thyroid cancer, is what are the impacts that the thyroid has on the body? Well, it, one, stimulates just your overall metabolic rate. Increases your basal body temperature. This is generally through inducing metabolism, and so you're creating more energy. That energy is being released as heat, which raises your body temperature. It induces enzyme synthesis of a lot of the basal metabolic functions, like the sodium potassium pump. Um, Also plays a role in growth and development, as well as the stress response, which you can see right here. But another important factor is this negative feedback loop. So when the thyroid hormones are secreted, not only do they act on the target tissues, but they also have a negative feedback on the pituitary and the hypothalamus, where they inhibit the release of TRH and TSH. And we'll talk about why that's important later on in the treatment. It has dual function. And so looking at the tumor cells of papillary thyroid carcinoma, PTC is the most common thyroid cancer. It arises from the follicular cells. You can see right here, here's a picture of the general anatomy of a thyroid follicle. It'll be, here's the follicle itself. It's surrounded by follicular cells. And then in the middle, it has the colloid, which this would be the thyroid colloid, just the part in the middle. And then when you have the tumor cells, there will be gross changes to the cells. You can see them right here. They're in gray. They're larger. They will have distinct like nuclear changes, like the size of the nucleus will change, the shape of the nucleus will change. You can have something like glassy nuclei that will happen, as well as gross changes in the chromatin structure. And I'm trying to display that right here. This is a picture taken from an actual papillary thyroid cells, and you can see that the gross changes to the thyroid follicle from being papillary thyroid carcinoma cells from those tumor cells. Also, thyroglobulin is a marker because it's secreted by follicular cells. So if you want to measure, let's say you remove all the normal thyroid cells and you only have cancer cells left theoretically, if you still have thyroglobulin, well, then that's a marker showing that you still have those tumor cells still in the body. So let's see. Another thing is that they can easily spread. You can see right here that if these thyroid cells were to break off, they would lose their adhesion molecules. Then they could gain the function of metastasis of spreading. You can see here through the lymph nodes, or even to this red right here is supposed to be showing blood vessels. Diagnosis of PTC is generally through fine needle aspiration, where they go in and they stick a needle and they sample the tissue. Let's say you have a growth, your physician palpates your neck and feels a growth on the thyroid. Well, they'll palpate it and they'll say, oh, we need to examine that. They'll do FNA. They'll do cytology, maybe some molecular testing where they can examine those cells and get a diagnosis. And in this case, we're talking about papillary thyroid carcinoma. So when we talk about cancer, we're really talking about what are the microscopic changes that happen within the cell, generally involving cell signaling. There's something that's gone awry. And in this case, I'm including the RAS-MAPK pathway because this is one of the pathways that are most commonly in thyroid cancer. And one of the most common mutations that happen is V600E in the BRAF protein. I'm including this signaling pathway. You can see on the left side, this is normal. And on the right side, this would be what happens under the conditions of a tumor cell. And so in normal conditions, there's some sort of external stimulus or signal, maybe like TSH, or maybe it's some other signaling molecule that says, hey, we need to induce survival, proliferation, or whatever the genes may be. And so it binds to the receptor, it induces that into the language of the cell. In this case, it's this pathway. BRAF will turn on MEK, which will turn on ERK, which will go and signal those transcription factors like FOS to induce survival, proliferation of those cells. If you have this mutation right here, you can see that there's no signal. And so this pathway is just constitutively turned on. And so this survival and proliferation are unchecked, increased. And this is in the absence of an external signal. So we can turn the pathway on, but we can't turn it off. And this would leads to those sustained proliferative signaling conditions, enabling some other hallmarks of cancer that are within these tumor cells are replicative of mortality, which means that the cells just continuing to replicate. Generally, they can extend their telomeres. This is a more complicated conversation than this presentation. Another one is resisting cell death. So whatever the signals are to induce apoptosis, programmed cell death, the cancer cells, the tumor cells can evade those signals through a variety of mechanisms to prevent those tumor cells from dying. So they can continue growing, continue proliferating, they continue replicating, but they can't die. And so this is why we have such a problem when we have tumor cells that are growing within our body. Let's see. So let's talk about treatment. So the first treatment is obviously to resect the tumor. And so the first thing that happens is you'll have what's called a thyroidectomy, a removal of the thyroid gland. Even if you have a small mutation in maybe one side of the one lobe, let's say like the left lobe, most surgeons will recommend you have a total thyroidectomy, so they remove both sides of it. The reason why is research has shown that if you have even a small one with no hint that had spread to the other lobe, and you try to keep it just to keep the normal signaling, the normal function of the thyroid, most of the time it has spread, the cancer will come back, and this is obviously bad. So they generally recommend total thyroidectomy. If there is any spread to like the lymph nodes, for instance, they'll remove those lymph nodes, and that's called a lymphadenectomy. And so they'll generally have a wide margin. They'll kind of clean out all the lymph nodes in the area that suspected or that have calcifications or whatever the indications may be that it has cancer, has tumor cells. The second thing is radiotherapy. And so specifically radioactive iodine, this is a very specific treatment for it. Going back to what we talked about in the beginning, you have the sodium iodine co-transporters. And so the follicular cells are cells in your body that can selectively uptake iodine. And so in this case, if we give radioactive iodine, we removed all the normal tissue. We've removed, not all the normal tissue, all the normal thyroid cells. And so whatever's left is automatically cancer, is automatically a tumor cell of the thyroid gland. And so if we give radioactive iodine and it's selectively uptake, well, that's great, because we can be specific in the fact that when that unstable nucleus within the iodine decays and that energy is released, generally beta or gamma waves, it selectively destroys those tumor cells, which is awesome. It's specific, it's effective, and causes that DNA damage and the apoptosis, programmed cell death of those tumor cells. This is what I'm trying to show right here. The third kind of treatment for it, which is something we generally don't think about as a treatment, but kind of is the thyroid hormone supplementation. So after we've removed the thyroid, we remove the gland that produce thyroid hormones. And we've already talked about how important these are just with your basal metabolic activity that's in your body. So it's really easy to fix, actually. We can just take levothyroxine, or it's just synthetic T3, and it's in a pill form. It's really easy to take. You can get your levels checked to make sure that your thyroid hormones are in acceptable levels. And honestly, most people, when they get older, they have a decline in thyroid function. So it's not uncommon for your grandparents, for instance, to be taking levothyroxine, or also one of the brand names is Synthroid. And so one of the benefits that we talked about, that I kind of alluded to beforehand, was this negative feedback. And so if you have a little bit higher than what you need for the thyroid hormone that's circulating within your body, it acts as a negative feedback to the hypothalamus and the pituitary gland, which can still release TRH and TSH. And so if you do happen to, after the thyroidectomy, after the radiotherapy, have malignant cells remaining, the added benefit of the supplementation with thyroid hormone is that it acts as a negative feedback to suppress the stimulation of TRH and TSH. And if you have very low levels of TSH, any remaining tumor cells are not going to be stimulated by the TSH anyways, because there won't be any around. So it will kind of be suppressing if you still do have tumor cells remaining. Beyond that, that's pretty much it. I hope you enjoyed my presentation. I didn't have any questions on the Moodle site from any of the students. If there are any questions, I'm happy to answer them. I think this is an important topic, especially because of how prevalent thyroid cancer is. And yeah, thank you for your time and your attention. And if you have any questions, email me. And other than that, I hope you all have a great day.